In exercise 1510, it says, for each of the following IR spectra, determine whether the spectrum is consistent with the structure of a ketone, an alcohol, a carboxylic acid, a primary amine, or a secondary amine. So those are the options, and we're going to be given spectra that we have to match to one of those. All right, anytime you run into a spectrum, always draw that line at 1500, vertical line. Everything to the right of that line are shadows that are cast by single bonds. So those are all single bonds there that are being cast. Another useful place to draw a line is at around 3000. So 3000 vertical line. And immediately to the right of 3000, you'll usually have a dip. That dip is between an sp3 hybridized carbon and a hydrogen. An sp3 hybridized carbon is a carbon that has all single bonds, and so that would just represent an alkane. So somewhere you have a carbon with all single bonds with a hydrogen on it. It's a common occurrence in an organic molecule. So you'll usually have that blue peak there in your spectra. Last but not least, we've got a sharp peak here. And if you look, it's 1500 is over here, then 1617. That's at around 1700. So 1700, that absorption is all by itself, it would be a ketone. And it says 1720. That's true. Maybe if you zoomed in, you'd see it's slightly to the right. You can see it. I had to put a little bit of a zigzag here. So it's slightly to the right of 1700. That sharp peak is a ketone. That's the bond from a carbon, double bond between a carbon and an oxygen. And so the structure of this is going to match a ketone. We know it's not an alcohol because an alcohol would have a smooth absorption between 3600 and 3200. We know it's not a carboxylic acid because a carboxylic acid would have that ginormous absorption that takes up like a third of the spectrum in addition to having this. And the ginormous absorption is representing the OH on a carboxylic acid. We know it's not a primary amine because that absorbs, both that and secondary amines absorb between like 3350 and 3500, and we don't really have anything significant there. So it's a ketone. All right, next one. So here, we have a new IR spectrum. First thing you do, draw that vertical line at 1500. It might seem like we're ignoring these single bonds all the time, and I guess that's true. So you might wonder why even include these. And it's because this region here, with all the single bonds, is unique to each molecule. And so if two molecules have all the same functional groups, you can tell them apart because they'll have different fingerprint regions. It's usually easier for a computer to do, but you could do that. Okay, so we have two other like little dips here, shadows. Our first shadow is a sharp one right there, and that shadow is, here's 15, 16, 17. It's just to the left of 1700, I'd say maybe 1720. That is a carbon to oxygen double bond. Then we have another absorption. It's a really fat one here, really wide, pretty smooth. That absorption goes from around 3600 to 2200. That is a that's the OH in a carboxylic acid. That would do that. Notice, if you look down at the carboxylic acid, we have 22 to 3600, really broad, and then at 1700, you've got this carbon to oxygen double bond shadow. And so you put those pieces together, you've got your carbon to oxygen double bond, your alcohol here, and that's what gives you your carboxylic acid. Just for the sake of observance, you might say, smooth, huh? Doesn't seem so smooth, not right here. What's going on? Well, if you remember that other line we usually draw, useful one at 3000, you'll notice that those bumps are happening just to the right of that. And those, if you recall, those bumps are those shadows are being cast by the bond between an sp3 hybridized carbon and a hydrogen, just to the right of 3000. I know this says 3000, it's almost always just to the right of that. All right, so what we have here is carboxylic acid. Done. Next. So we have a new spectrum, draw a new line at 1500. Everything to the right of that. All of this represents single bonds. So a bunch of crazy single bonds in that molecule. Another useful line is around 3000. And the reason it's useful is because just to the right of it, you have that very common absorption caused by sp3 carbons to hydrogens. It's just to the right of 3000. So not really a functional group there, but it's a landmark. And now we have this other kind of, I guess it's big enough to be a dip, right? It's not like as small as this little thing over there. Remember that you're always comparing these, even if you look at these different spectra that the book is making, and the book is trying to make them look nice because you're learning on these, the line changes. It's not always at the same place. Here it's around 70, here it's above 80, right? So that line will change depending on the solvent you use, depending on how you prepare your sample, even depending on the machine that you use. So what you're looking at is not so much the specific numbers here as how far do things go down relative to that line, and are those dips in places that I know to tell me about specific bonds? Do they line up with what's on this table? So here we have an absorption here, and it kind of goes between 3500 and, 33 or so, maybe 3200. You've got that absorption there. It's mixing a little here, so it's kind of hard to say where it ends. But you have that there, and that is a dip that's being caused by an amine. Now another sign that this is a dip to an amine is the fact that it doesn't go down very far. The further these go down, the bigger the shadow, the darker the shadow they're casting, the better they're absorbing or responding to light. And things respond better to light the bigger the dipole is. But these bonds respond better to light the bigger the dipole is. So something like oxygen to hydrogen, oxygen's very electronegative. It steals the electrons from hydrogen, gets a really big slightly negative charge, and the hydrogen gets a really big slightly positive charge. Look at the periodic table though. Electronegativity increases as you go up and to the right, and in the top right you have nitrogen, oxygen, and fluorine. Oxygen is more electronegative than nitrogen. So if you have a nitrogen to hydrogen bond, which is what you have in these amines, an amine is a functional group that has a hydrogen with all single bonds around it. If you have that hydrogen, it still is electronegative and it still will have this slight negative charge. It just won't be as big as it is on an alcohol. The negative charge on an alcohol is bigger than the negative charge on this nitrogen. And because the charges aren't bigger, it doesn't respond to waves of electricity as well. It'll still respond to them a little bit and absorb them, and so you still do get a dip here. But it's not as big of an electric charge. These are not as big of electric charge as these, and so it doesn't go down as deep as an alcohol would. Okay, so those are your two signs that you have an amine. It's in the general area between around 3350 and 3500, and it doesn't go very far down, certainly not as far as an alcohol would. So that's an amine. Now, the amine only has one dip at the end. You see this dip right here. And that amine is a sign that you have a secondary amine. A primary amine is one that's only bonded to one carbon. The other two bonds are to hydrogens. And those two hydrogens can move in different ways together. That would cause two dips. A secondary amine is an amine that has two carbons. So there's only one hydrogen here, and it's that nitrogen to hydrogen bond that's causing this one little dip there. Oops. Okay, so what we have here is not just any amine, it is specifically a secondary amine, because a secondary amine is the one that has just one dip. The primary amine would have two dips in this area. For example, in this new structure, first thing you do when you get to an IR spectrum, draw that vertical line at 1500, right here. And we have some things to the left of that. The first thing we have, we have like these little peaks here. And those are at positions that may or may not be relevant. It looks like you could possibly, maybe, this looks like it's between 16 and 1700, that. And so it's not going to be a ketone. It wouldn't be a carbon to oxygen double bond. That is either at 1700 at the lowest, maybe a little further in most molecules. So that is going to be a peak that you're not responsible for right now. Not on this table here. Okay, so we have a couple other ones. Draw that other second useful line at around 3000. Just to the right of that, you have this very common absorption. That's the shadow being cast by an sp3 hybridized carbon to a hydrogen bond. And then we have a little peak here. It doesn't go very far down, and it's around 3500 and 3350. And so that is going to be an amine. It doesn't go very far down, around 3300, 3350, and 3500. And if you look at the tip there, there are 2 little dips. And it's those 2 dips that I'm referring to here in this table, 2 dips between that. And so really what we're dealing with is a primary amine. So here we have a nitrogen. A primary amine is only bonded to 1 carbon. You have those 2 hydrogens. It's those 2 hydrogens that are giving rise to those 2 little dips there. Okay. Remember, everything to the right of 1500, that's representing all of the single bonds. And there we go. All right, next one. You have a new IR spectrum. That means you get to draw a new line at 1500. Everything to the right of that are shadows cast by single bonds in the molecule. So they merge together, they're hard to read, but they're unique to each molecule, so it's the fingerprint region. And then another useful line to draw is at around 3000, because we know just to the right of 3000 we have that famous, maybe by this point infamous, shadow cast by sp3 carbon to hydrogen bond. We have an absorption at around 1700. So notice it's 15 here, 16, 17, maybe a little bit higher than 17. And so that would tend to suggest a ketone all by itself. And those are the only absorptions we have. So there we go. All the evidence we have points to ketone. Now technically it could also be an ester, but notice that an ester was not given as an option in the question. The question said, for each of the following IR spectra, determine whether it is consistent with a ketone, alcohol, carboxylic acid, primary amine, or secondary amine. Nowhere do they mention esters. There are other ways to determine to distinguish between whether you have a ketone or an ester. But for this specific test, you won't have to worry about those. You just want to be able, either a ketone will be an option or an ester will be an option. I'll never make you choose between them. So here, the only option would be a ketone. All right, F, our last spectrum. So, a new IR spectrum, it's a new opportunity to draw that 1500 wave number line. everything to the right of that, is representing single shadows cast by single bonds. And to the left, we've got a couple shadows. So draw that second useful line at around 3000. And remember, just to the right of that, this absorption here, that shadow there, is a shadow being cast by sp3 to hydrogen, sp3 carbon to hydrogen bond. That's a carbon with all single bonds. And we have one more absorption. That absorption is this smooth absorption here, and it seems to be from about 3600 to, 3200. And that is the sign that you have an alcohol. That is the shadow being cast by this bond here between an oxygen and a hydrogen, as you would have in an alcohol. And so here, all signs point to having an alcohol. So this was some practice just with sort of marking off different parts of an IR spectrum and just getting used to identifying some fundamental functional groups in that spectrum. And from here, if you choose, you can learn even more, you can get more nuanced, but this is a foundation for you to build on for reading these IR spectra.